So we'll start off with what is a linear programming problem. So an LP, so first this page, let's give a basic explanation. An LP consists in trying to maximize or minimize an objective function and such, and you generally get it as max or minimize a z, the green stuff, x or minimize z here in green. And you get a linear combination of decision variables, which are all, x's. They're generally represented just by x1 and such, x2, x3, x4, xn, any number of x variables. And that's why you have constants times them. Like that's what the max and min function is generally. And you have such that, usually abbreviated was ST, such that like S period, T period. You get constraints that can, you have the max objective function, here, which can be a maximization or minimization of Z. You have constraints that go from A1 to X1 plus etc. all equal to B1. Similar to linear algebra, you can have like you can have like a linear system represented in a matrix sort of way. Well, not fully matrix, but it's like that, where it's like a linear system of equations would be the first parts are like A1 x1 plus A2 A1. It's A11 x1, so it's sort of like almost like a matrix. How it's represented. It's analogous to it. It's not a matrix, but it's similar to idea. Yeah, you have A12 x2 plus plus an times xn, and you have less than or equal to, or greater than or equal to, or equal to b1. Same goes for all of them until you get to a. The last row was am1 x1, eventually to amn xn, less than or equal to, greater than or equal to, or equal to bm. You know the crossed out stuff. So the constraints are that, and then you have, generally speaking, you have x1, x2 to xn greater than or equal to 0 is a very common constraint. Strict unit. And generally speaking, you're restricted to positive x variables. So that leaves you in the first quadrant of the xy axis, the two-dimensional grid. Or a further grid, like you're basically stuck with positive values in most cases, basically. Let me first look at two-dimensional, but there's more. There's 3, 4, 5 variables I can't graph, but generally speaking, this does limit two variable ones to one quadrant. Then you have just the definition of AIJ's technological coefficients, if we use in technical terms, and B1, B2, BM are right-hand side of constraints. Of course, because saying it's similar to a linear system of equations, except for its inequalities here. And the feasible region of an LP, it's usually inequalities, at least with these, but there's ways to modify it. Eventually, later on, you'll see that you can make them equal signs. You can make an inequality into an equal sign. There's a way to do that. But that's for more complicated things. And the feasible region of an LP is just all values for the variables that satisfy all constraints. And it's a region meaning that there's multiple different conditions in most cases, that would satisfy the constraints. Then you have to figure out what the optimal solution is, which is the maximum, what's max or minimizes the function z. An optimal solution of LP, of course, now we'll say, is the values in feasible region that are maximizing or minimizing z. What was you saying? But that's enough for explanations. Let's look at like a couple examples, like one main example and like some scenarios with feasible region. So we're not even solving it here. We're just looking at it. We'll solve it in another video. Farmer Jones must determine how many acres of corn and wheat to plant this year. I think that's good. You can see it here. So it's lawn palm, takes up the whole paper. Because I wrote it in big text to make sure you can read it. Point is, you have 25 bushels of wheat that require 10 hours of labor per week. He's trying to figure out how many acres to plant, basically, and you have an acre of wheat doing that. An acre of corn yields 10 bushels of corn and requires 4 hours of labor a week. So those are two main things. And you have this, how much they can be sold for. All wheat can be sold at $4 a bushel, and all corn can be sold at $3 a bushel. And that's all the important stuff in the problem, really, like that gives you what you're going to use for your numbers and such. Oh, and we also have this 7 acres of land and 40 hours per week of labor available, so that's constraint. You have your land constraint, your labor constraint here if you want to give titles to it, which you often will do, but this time I don't, but basically that's important to note. Oh, and here's another constraint, government constraint. Government regulations require that at least 30 bushels of corn be produced during the current year. I'd underline these, but like I already got the things that are really, really big. I think these are pretty obvious, the constraints, and we'll see. So we need a minimum of 30. At least is minimum. Like it means at least would be not minimum. It would be less than or equal. Greater than or equal to. You'd have an at least means you want the bare minimum 30. So you have a greater than or equal to 30 will be involved. And when it's only how much are available, then you'll be less than or equal to generally. So you have these to be less than or equal to 7 acres of land. So you have to have at most. You'd have at most 7 acres. So it has to be less than or equal to that. And then it says in the problem, let x1 equal number of acres of corn planted, and x2 equal number of acres of wheat planted. And using these decision variables, formulate an LP whose solution will tell Farmer Jones how to maximize the total revenues from wheat and corn. So you do a table, especially when you're early on, you especially do these. Usually a table helps set it up. So crop is wheat or corn, and we have revenue per bushel first. So that's $4 a bushel for wheat, $3 a bushel for corn. So 10 hours versus 4 hours. 4 hours corn, 10 hours wheat. As you can see, 4 hours of labor a week, 10 hours. And then we have how much is produced, how many bushels. 25 bushels for wheat are produced per acre, and 10 bushels of corn are produced per acre, as it says right here, and I copied out. And then we have in total 7 acres of land available, 40 hours of labor a week available. So you have land, 7 acres of land, 40 hours labor, and 30 bushels of corn a week must be produced, no matter what. So max z equals 4 times 25 x2 plus 3 times 10 times x1. So we have to create our objective function as well to start off. And we know it's because it's revenue. Our objective function is giving us a profit, so in this case, we have to figure out how much you're making per bushel, or per acre of land, in this case. So x1 and x2 are bushels, so real quick, just make sure x2 is the number of acres of wheat, x1 number of acres of corn. So $4 per bushel wheat, so 4 times 25 bushels, because that's how many are produced per acre. So revenue per bushel times produced per acre, the bushels per acre, gives us basically what our revenue per acre will be. So it's 100 revenue per acre of wheat, so it's 100 times x2. So x2 acres, and same with $3 per bushel times 10 bushels an acre gives us 30x1. And that's our maximizing z function, our objective function as it will. And the constraints are found just x1 plus x2 less than or equal to 7. Like I said, that's very obvious from the problem. We have so acres of corn is 4 times x1, acres of wheat are 10 times x2, as we said before. From here we saw. So that means that 4x1 plus 10x2 is less than or equal to 40 because only 40 hours of labor a week available. And it's $4 per bushel, and we're trying to maximize, we do the dollars per bushel and the acres alone. Oh, no, the hours per acre. Yeah, because it's labor constraint, it's 40 hours, it's less than or equal to 40 hours, so this goes into 40 hours. So 4 hours for corn, so 4 hours times how many acres, and 10 hours times how many acres of wheat. So that's why it's 10 times x2 and 4 times x1. And that's 4x1 plus 10x2 is less than or equal to 40. So that's a big constraint. That's the one you have to do the most work for. And then finally, 10 bushels of corn times however many acres of corn you have has to be greater than or equal to 30. So it's 10 times x1 because you get 10 bushels of corn per acre here. And you need 30. You need 30 acres of corn a week. I mean 30 bushels. Sorry if I'm mixing up terms, but it's in Ren as well. So 30 bushels of corn a week means that we have to have 10 bushels. We get 10 bushels per acre, so 10 times how many acres, which is x1 of corn, is greater than or equal to 30. And basically, if it's not obvious, it's going to be that's a very simple one. You're basically going to want 3, but you'll see that when we solve it, the graph for that will show that. We're not solving it this second. We're just setting it up. So cropland, hours to farm, 1 acre, and constraints, we can write again we can write it as a smaller table. So we have x1 acres of corn, x2 acres of wheat, hours to farm 1 acre, 4 and 10 from before. And these each have to be positive values, or they have to be greater than or equal to 0, so positive or 0. And x1 plus x2 less than or equal to 7. So our final LP is as such. As I did before, we have a max from before, 30x1 plus 100x2. Then we have a land constraint, x1 plus x2 less than or equal to 7. A labor at 4x1 plus 10x2 less than or equal to 10. The hours to farm on board. And we have 10x1 greater than or equal to 30. The amount of crop we get from corn. Then x1, x2 greater than or equal to 0. Always include that as whatever your constraint on the variables are. And that's our LP. That's the solution. So now we answer these questions about problem 1, which is just the feasible region. So is x1 equals 2, x2 equals 3 in the feasible region? Well, it's not, but first you have to check every condition. So you get 5 acres of land, which is good. You get 38 hours of labor used, which is good. It's less than 40, so that checks. 10 times 2, though. 2 acres of corn. My 2 acres of corn, right? It's like, you see, because x2 is equal, so x1, remember, x1 equals number of acres of corn land, and x2 equal number of acres of wheat. And we need, but basically I was just saying, we need 30 acres of corn, 30 bushels of corn. So 2 acres of corn is not enough. That equals 20. 2 times 10 is equal to 20. So so it's not in feasible region. That's not, so x1 equals 2, x2 equals 3 is non-feasible region. Is x1 equals 4, x2 equals 3 in the feasible region? Well, we have 7 acres. We have 7 acres, right? So that's less than or equal to 7. It's equal to 7, so that works. 4 times 4 plus 10 times 3 is equal to 46, which is greater than 40, so that does not work. That's not in feasible region. x1 equals 2, x2 equals negative 1 in the feasible region? No, this is not either. Because x2 equals negative 1 and x2 has to be greater than or equal to 0, so the constraint fails, so it's not in feasible region. And then we finally have x1 equals 3, x2 equals 2 in the feasible region, and this one actually is. 3 plus 2 equals 5, so that works. 4 times 3 plus 2 times 10 gives us 12 plus 20, which equals 32 hours of labor, so it's less than 40 hours of labor. That works. 10 times 3 equals 30, so we have just enough corn. So 30 bushels of corn is just the minimum it needs. So, yep, we are equal to 30. And 3 is greater than 0, 2 greater than 0, and that checks off. Just as a double check, it's like, so x1 equals 3, x2 equals 2 is in feasible region. And that's it for this topic on just the setting up, just showing off the basic setup of an LP and some of the properties.